Hello, everyone, and welcome to Powering Experiences, brought to you by Samsung Semiconductor Inc., a podcast where we sit down with leaders in the field of semiconductor memory, storage, processors, sensors, and everything in between to take a closer look at the intersection of advanced technology and everyday life. I'm your host, Nick Stoll, and today I'm with Radwan Siddique. Now, Radwan is definitely a smart guy. He's our team lead for bio-inspired engineering and biosensing in our image sensor lab. And he got there because he has a bachelor's in electrical engineering, and on top of that has a master's and a doctorate. He's been doing research for a lot of years now, and a large focus of that research has been on naturally occurring phenomena in organisms and how that translates to technology. Welcome, Radwan. Bio-inspired nanophotonics isn't something you hear every day. Maybe you could start with some background and a definition of this type of research.
Okay, hi. Thanks, Nick, for the nice introduction. So yeah, my research interest focuses on bio-inspired nanophotonics. So you already mentioned that. So we work on metaphotonics, which is basically the engineering of optics and light with micro and nanostructured materials, so that we can engineer how the light flows and control basically the light propagation. So this, which is interesting for most of our sensing application, optical-based sensing applications. So if you notice that I mentioned already that so we work with micro and nanostructured materials for molding the light, but the nature has been doing that for millions of years of evolutionary process. So these butterflies, or there are lots of butterflies or insects, they create the colors using micro and nanostructured materials on the scale lengths. So what we are suggesting is a new field of research. Nature has been doing it for millions of years. So the idea behind of research into bio-inspired nanophotonics is, so why not use nature's engineering skill sets or the background, which nature is awesome at engineering, and they have been using the millions of years of experience. So why not just use it, learn it, and implement it in our technologies? So that's basically the motivation behind of bio-inspired nanophotonics.
I love the idea that nature is awesome at engineering things itself. And what are some of the ways that you can bring those concepts that naturally occur in nature into your optical sensor technology research?
Right. So we work on sensors and imaging solutions for Samsung Semiconductors. So we make nano microstructured devices for specific applications. And for some of the applications, we kind of use the similar kind of patterns what nature offers. So what we try to do is we try to pick and learn and I would say, imitate some of the the tech what nature offers and kind of optimize it for our specific applications.
You just mentioned applying patterns that nature offers to your research. Can you expand on that idea a bit and maybe delve into your specific research with butterflies that you alluded to earlier?
Right. Yes. Just to give you some examples of what I did before. For example, I worked on a black butterfly. So these black butterflies on the scales, they have some sort of nanostructures which help them to absorb light efficiently. And if you think about it, and for our different applications, for example, in our photo detectors for our for cameras, which basically absorbs light and turn into photoelectrons, which basically gives you the images. So just think about like straightforward. I mean, if you know, so the butterflies are so efficient at absorbing the light. Why not just use the same technology in our photo detectors for absorbing more light? So that's kind of like, it's like kind of one-to-one correlation. So basically we can learn from butterflies how to absorb light more efficiently and make our photodetectors better at absorbing light so that it can create highly efficient, higher signal to noise ratio photoelectrons, which basically we see as images afterwards.
Just to be clear, which part of the butterfly are you referring to? Its wings, correct?
Right. So we are not specific about the parts of animals. We are interested more about like the functions of those insects and what function can be useful for our applications. So this is one of the example I mentioned. So like the wing basically absorbs like light, and that can be directly correlated with photodetectors, because photodetectors basically absorb light and convert into photoelectrons. So it's like one of the applications what I'm mentioning here. But also, like for example, the butterfly eyes. Some of the butterfly eyes, they can differentiate spectrum of light. For example, human, we have only blue, green, and red cones, right? So we can see blue, green, red. So that's three cones specifically. But then in butterflies, they can see UV, which we can't see, for example, as a human. Sometimes some of the butterflies, they can see NIR. So they have a broad spectrum of range they can see. And those spectrum of range could be interesting for imaging applications. For example, in some of the cameras we use in our smartphone, they use NIR, for example, like near infrared light. So, so that's what we try to imitate the properties of butterflies. It could be the spectrum. It could be the different kind of light properties, basically.
Understood. In addition to butterflies, are there other examples of this type of advanced nanophotonics in nature?
In fact, there are. I mean, so as you mentioned, so about the vision, right? So I mean, for example, like we know that night animals like cats or owls, I mean, they can see better. They can see better in the night than us. That means their vision is kind of optimized for low light imaging, right? That's why they can see better than us, like humans, at night. So we can probably learn from those vision, like how they are better, how their vision is so nice for low light imaging. So that's one of the examples I'm saying. Then there's another example of, for example, a wiper, right? So wiper peat. I mean, they can detect thermal changes in terms of RGB imaging. So they have like a hybrid vision. So they can see visible color like us, what human do, but they can also detect temperature changes. So they have a thermal vision. So and their thermal vision has like one of the best thermal vision camera they have in not in nature but in world. So probably we can learn how they can detect such small temperature changes, which probably we can use for making highly efficient thermal camera, for example. So yeah, so different. I mean, so different animals or insects can give us like different kind of camera concept.
And then when you take those properties like NAR or UV light or that thermal imaging and apply it to technology that's used by people, how do we leverage that type of technology to our benefit?
Right. So what I like about this nature or bio-inspired vision is, so usually nature always comes up with simple solutions. So they have a simple solution. It's so elegant. It works for in so many versatile conditions. For example, think about our one of the butterflies I mentioned, right? So they can detect UV, ultraviolet, visible, RGB, also near infrared, but they have single lens. They just have one single lens which can detect all the spectrum. However, in what as an engineer, as an optical engineer, I know that it's such a complex technique to make single optical lens to see this broad range of spectrum. I don't know, have you seen this DSLR camera, right? I mean, they are so big. It's because they have a kind of system of lenses. With a single lens can't do all this thing. If you have just single lens, there will be lots of aberrations, distortion. But think about this nature. They have single lens and they can see clearly such a broad range of spectrum without aberrations, distortion. Even our human also, they have single lens. But our cameras have so many lenses just to fix one aberration, another aberration or distortion. So nature always comes up with simple tricks to solve complex problems. So that's what we try to learn, how we can make our system simple. Because if you make it simple, that means it will be less, like, cost effective, more versatile, will be more compact, right? So so that's what we are aiming for, trying to make compact, high performance solutions, optical solutions for our imaging and sensing applications.
And when you're doing that translating to technology, um, you kind of talked about, mimicking it, but in what ways do you have to approach it with an eye of changing it or altering it slightly so that it fits a kind of somewhat different purpose once we're seeing it in the tech?
Yeah, that's a really good question. So you are right. So, for example, I'm saying nature use single lens, but right, so it's made of organic materials, for example, right? But then when we make our sensors using semiconductors, right? So it's not anymore organic; it's an inorganic materials. So definitely, we have to translate we learn from nature, and we have to find a way how we can translate it in our current fabrication techniques or manufacturing techniques. So it's not like a kind of apple to apple translation, I would say. So that's why we don't. So there's a term called biomimetic and bio-inspired. So when we say biomimetic, that means it's directly mimicking bio, right? But here we say bio-inspired. The reason we get bio-inspired because yeah, we are learning what nature does, but we are trying to implement it in our way, what we have in our current, manufacturing abilities, or how we can implement it as a best way possible.
I see. That's some really fascinating stuff. And so I was wondering, was there kind of an inspiration, so to speak, to go into that field of study? Like, can you pinpoint the exact moment you decided to devote a large majority of your adult life to this kind of research?
Seriously speaking, I had no idea about it before I started my master's. So I wanted to learn more about optics because when I was doing my electrical engineering, I can see that the field is going to be the semiconductor field is highly dominant, going to be dominated by photonic engineering. So the electrons are going to you know, going to replace by photons. So everything needs faster, compact. And then during my master's program, I was attending a summer school where there was like different professors and researchers representing different aspects of photonics research. And there was like one professor from so his name is Professor Vukusic, Pete Vukusic. So he's from University of Exeter. So he presented a talk which basically talks that about this, amazing nanostructures what nature has and how they manipulate light and make nice colors. And then I was like so amazed with it. I mean, I never imagined like so what we call like the 21st century technology, nanotechnology, and all this stuff, and the nature has been doing it for such a long time. So I was like so amazed, and then I just directly went to that professor that I want to learn more about it. And then he kind of guided me to the professor in my university that there's one professor who's exactly working on the same field. Then I just immediately went to that professor. I said that no, I want to learn more about it. It's such an amazing thing that what we are doing, nature has already done it, kind of thing, right? So yeah, so why not just learn more about it and exploit it for technology? Yeah, so that's how it started. So it's just like one nice talk from a professor and kind of like changed my life, I would say.
What are some other examples of uh, phenomena in nature that you either have studied or want to study, or maybe other people are looking at those other phenomena and applying it to their research and their technology? And what are some of those things that you found particularly interesting?
Right. So as I mentioned, I'm an optical engineer, so I'm more interested on what kind of optical technologies we can learn from nature and bring it to the semiconductor level, right? So, for example, like one of the problems. So our team they work on depth sensing using lidar, and some of the problems they're facing is, for example, if the weather is bad, if it's foggy, right? They don't get enough information, right? The light information. Uh, Another example is if it's a black object, right? When you don't see much information, so they can't detect the depth information. So these all are optical problems. But nature, some of the nature, they kind of find a way to solve these problems. For example, there's a mantis shrimp. So they live in under the water, right? So under the water, usually what we say is the contrast, the refractive index contrast is really low, which means that it's hard to detect objects or differentiate two objects that easily. So they use it's called the light polarization. So polarization is a property of light which human doesn't we don't see the light polarization, but probably you heard about the term polarization because if you work with cameras, usually you use polarization filters, for example. So this mantis shrimps, amazingly, they use the light polarization properties to differentiate objects, different objects, or if there's like low light, for example, if it's foggy or like not foggy under the water, but I don't know, like scattering, they can't see it properly. But then the light polarization is completely uninterrupted with this, foggy and all these details. So light polarization can be useful for detecting, this hidden information, or if it's small, if it's foggy or there's a smoke. I mean, you can get the information through the light polarization. So, so that's we can learn from Spanish shrimp, like how to image obscure images or obscure objects, which is hidden under a fog or rain, for example. So that we can basically translate to our lighter problems to image objects which you can't see it in, bad weathers, for example. But then there's also different other examples, as I mentioned, spectrometer, spectrum, right? So we can see only red, green, blue, but some of the nature they can see so many other colors. And sometimes this specific colors can give you more information than other colors. And that can be used for example, material detection. When we talk about robots, right, or computer vision, or vision of drones. So for them, it's really hard to detect transparent object, right? I mean, they don't know whether there's a transparent object because light passes through, and then you don't know whether it's a glass or not. But then if you use, this light polarization, you can easily differentiate transparent objects. So, which is amazing because for human, probably we can differentiate glasses, but sometimes it's even harder for us, even, right? I mean, if there's really clean glass, you will easily bump into it because you can't see there's a glass, right? The thing about the robots are drones who, I mean, for them, it's even harder, to differentiate glasses. I mean, they can easily bump into glasses, right? So, but then we can use a trick of mantis shrimp because they use light polarization to detect transparent objects. So that's one of the things we are also looking into it to detect glasses, which we can use it for robotic sensors and drones to make the vision more efficient.
And I believe you mentioned something in the past about spiders. Am I correct in saying that, or am I incorrect?
Yeah, that's right, exactly. So the spider for depth sensing, right? So spider uses special kind of nanostructured vision, I would say, for detecting depth. So so their technology can be really useful for depth imaging in also for us. So we also try to look into it, like how spider detects depth, and they can accurately detect depth within centimeter, within millimeter resolution, and which is pretty hard for, in fact, the regular lidar. I mean, the resolution of regular lidar is much more than millimeters. So, so if we can learn those techniques, how they can, resolve millimeter depth, so we can probably use this technique in lidar technology, for example.
Yeah, and I have another question about kind of how you approach this research. Does, when you shift between different um, bio-inspired solutions, is it you find something that you think is interesting and you bring it to someone and say, "Hey, I think this could fix this or help this," or does someone come to you and say, "Hey, we're having trouble seeing in foggy situations. What is something in nature that helps that? Can you figure it out?" How does that kind of work?
Right. No, that's a really good question because I always get that question because it's true, right? I mean, you can. It's two way. It's like a twofold, right? So either you can first go through like what's the problem in your tech and try to find solution in nature. But it can also be vice versa. Like if you know what's the solutions you have in nature, then you can think of how you can solve the problems in tech. So that's a really good point. So we have in Image Sensor Lab, so we have a really diverse team. So we have experts in, computer vision, experts in AI, image signal processing, mechanical engineers. So we have people from different skill sets. And so what I'm optical engineers, and I did a lot of research on this bio-inspired optics throughout my, I would say, as you mentioned, last 10 years. So I know lots of the, solutions, how what nature offers. And so when I, try to find out what other difficulties we are facing for our products, for example. And for me, it's easier to connect because I have previous, prior experience on this bio-inspired photonics. So then for me, it's easy to, connect them and try to find solutions out of it and try to implement it here in our, in our products. But definitely, I won't say I should not steal all the credit because we have a diverse team. We kind of like start the discussions and try to dig in deep and then try to find the best way possible with the whole team, how we can, implement that, solutions what we have in nature into our products.
And is there something you would say that you wish everybody knew about optical engineering and how it impacts our daily life that you would want to tell the people listening to this?
Right. I mean, optics is everywhere. In fact, all the uh, most of the current sensors. So we work with sensors and imaging. When we say imaging, it's about all optics, right? So what we see, it's all the light electromagnetic spectrum, which is usually it's the visible light, red, green, blue, or white. So that's optics, right? And the sensors we deal with nowadays, right? The machine vision sensors, it's all are optics driven. Most of the sensors in the smartphones are optics driven, which utilizes light basically. And then so that's why I mean that's one of the reasons as I mentioned, I was fascinated. I was trying to move towards optical engineering. Although I studied electrical engineering, I felt that yeah, the next technology is going to be optics driven, photonics driven, because we can't make the electronics faster much. You can do that as long you can, translate everything from electrons to photons, because photons are faster, much faster than electrons. So that's the new technologies, going to be driven by optical technologies. So, I mean, that's why my motivation was why we should study optics, and I hope, yeah, I mean, I mean, the next generation or the current generations will be still interested to pursue optical engineering.
Well, thank you, Radwan. It has been a pleasure talking with you. You've been listening to Powering Experiences, brought to you by Samsung Semiconductor Inc. The show's executive producer has been Melanie Nelson. Producers include Lisa Warren Plungy and Danny Pugh, with creative direction from Andrea Karim. Until next time, I'm your host, Nick Stoll. I hope you learned something today.